Today we will learn triaxial compression test for cohesive soil. Purpose: the triaxial compression test, or simply triaxial test, is used for the determination of shear characteristics of all types of soils under different drainage conditions. The drainage conditions may be classified as follows: A. Undrained test or quick test, or unconsolidated undrained test (UU test). In such a test, the soil specimen is subjected to normal pressure. In lab, hydrostatic pressure is applied. Under undrained condition, both top and bottom drainage lines are closed. B. Consolidated undrained CU test or consolidated quick test. In such a test, the soil specimen is allowed to consolidate. Both top and bottom drainage lines are open, but is sheared without allowing any drainage. C. Drain test or consolidated drain test CD test or slow test. In such a test, the drainage lines are opened during both the consolidation and shear test to dissipate water from sample. Here shear test is carried out slowly so that no excess pore pressure develops in soil pores and all stresses at all times are effective or intergranular. For clay soils, the choice of the test conditions depend upon the purpose for which the shear strength is required. In case of sand, consolidation occurs relatively rapidly and is virtually completed during the application of the load because of high permeability of sands. So, tests on sands are generally carried out under drained conditions. Apparatus and supplies. Triaxial apparatus, specimen trimmer with wide saw knives, etc. Rubber membrane, de-aired water supply, balance, drying oven, desiccator, timer, etc. 1. Specimen preparation. A. Undisturbed specimen UDS. 1. Note down the sample number, borehole number and the depth at which the sample was taken. 2. Remove the protective cover paraffin wax from the sampling tube. 3. Place the sampling tube 38 mm dia extractor and push the plunger till a small length of sample moves out. 4. Trim the projected sample using a wire saw and push the plunger until a 76 long sample comes out. 5. Cut out this sample carefully and hold it on the split sampler so that it does not fall. 6. Take about 10 to 15 gram of soil from the tube for water content determination. 7. Note the container number and take the net weight of the sample and the container. 8. Measure the diameter at top, middle and bottom of the sample. Find the average and record the same. 9. Measure the length and weight of the sample and record. B. Remolded specimen. R. 1. For the desired water content and the dry density, calculate the weight of the dry soil Ws required for preparing a specimen of 38 mm diameter and 76 mm long. 2. Add required quantity of water Ww to this soil. Ww is equal to Ws into W divided by 100 gram. 3. Mix the soil thoroughly with water. 4. Place the wet soil in a tight thick polythene bag in a humidity chamber. 5. After 24 hours, take the soil from the humidity chamber and place the soil in a constant volume mold having an internal height of 76 mm and internal diameter of 38 mm. 6. Place the lubricated mold with plunger in position in the load frame. 7. Apply the compressive load till the specimen is compacted to a height of 76 mm. 8. Eject the specimen from the constant volume mold. 9. Record the correct height, weight and diameter of the specimen. Testing procedure. 1. The saturated porous stone disc of diameter same as the sample is placed on the top of the pedestal of triaxial testing machine. and the circular filter paper of same size is placed over the disc. Specimen is placed on the top of the filter paper. The filter paper with porous stone is placed on the top of the specimen to allow two-way drainage. The latex membrane is stretched in the membrane stretcher and placed on the soil specimen. O-rings are placed at top and bottom of platters of the soil specimen to prevent the cell water from entering into the specimen. 2. The triaxial cell is placed over the base and tightened with the screws. The cell is then filled with water and a small confining pressure of about 10 kPa is applied to hold the specimen in place. 3. The soil specimen needs to be completely saturated before isotropic consolidation phase. 4. Saturation process consists of 3 steps. 1. CO2 saturation. 2. Water saturation. 3. Back pressure application. 5. CO2 is applied continuously for minimum 3 to 6 minutes for bottom of the specimen and then allow it to go out of the specimen from the top. CO2 replaces the air in the void space of the specimen, which gets easily dissolved in the water present within the specimen. The CO2 flushing process is repeated 4 to 5 times to ensure better saturation. 6. Water saturation is done by supplying water from bottom of the specimen and allow it to go out of the specimen. From the top to do proper water flushing of the specimen. The water used for flushing needs to be distilled and de-aired water. 7. The forced saturation is performed by applying cell pressure and the back pressure at constant increments with constant difference between these two presses. The sample is allowed to saturate for some time, 10 to 20 minutes after each increment of cell pressure and the back pressure. This increase should be followed by a check for saturation value B, also known as Scampton's pore pressure parameter. It is important to note that cell pressure always is higher than back pressure. The sample is said to be fully saturated if the P value greater than 0.95 can be acquired. 8. Isotropic consolidation stage is started by applying confining pressure. During the consolidation stage, drain valve is kept open and the volume change is measured until no change in volume is observed when primary consolidation is over. 9. In unconsolidated undrained UU test, no drainage is allowed during application of confining pressure. In the consolidated undrained CU triaxial test, no drainage is allowed during shearing stage and pore pressure is measured throughout the test using the pore pressure transducer. In case of consolidated drain test CD, drainage is allowed and test is slow enough so that pore pressure do not build up. 10. The machine is set in motion at an appropriate strain rate based on the soil type. The experiment is stopped at around 15% axial strain.